Okay, in the previous section, we minimized the cost function. If you look at the sample homework problems, and it was subject to a constant volume. So we say it's subject to a constraint that the volume of the box was constant. Actually, it was an aquarium. Okay, well, here is another way to do that, and it's called using Lagrange, used a capital G, multipliers to maximize or minimize a function. And here I'll do 3 variables, but you can do just 2. Subject to the constraint, you have another function equal a constant. Okay, and let me just draw kind of a picture to explain this. Here's where, say, a function of 2 variables is equal to a constant. So that's the level curve. And then you have another function coming in here. And that's where it's going to be maximized, where they intersect. So the job of this is to find the largest C, just to find the largest level curve where G and F intersect. And this happens when where it happens, they have the same tangent line and normal line. So the gradient vectors are parallel here. And so since they're parallel, the gradient of f at this point, let me call this P0, at this point P0 is equal to some scalar, because that just decides the length, times the gradient of g at that point. And lambda scalar, lambda is called the Lagrange multiplier. Okay, and you can look in your text to see how it's proved. Okay, so to find max and min values, of f, constrained by g is equal to a constant, and the gradient of g is not 0 on g. Number 1, we're going to have to find the x, y, z, and lambda such that the gradient f is equal to lambda gradient of g, and the g of that x, y, and z is equal to that constant. So you set up these equations where f of x is equal to lambda g of x, f of y is lambda g of y, and fz is lambda g of z if you have 3 variables, and you have g of x, y, z equal to some constant. So you're going to solve these equations and get your points. And then 2, you're going to evaluate f at these points. The largest is the maximum value. The smallest is the min value. Okay, so let me do an example. F of xy is going to be 3x plus 4y minus 3, restricted by the circle. So this is g of xy, and this is our constant. All right, and this is our f of xy. So partial of f with respect to x is 3, and that's equal to lambda partial of g with respect to x. Fy is 4, and that's equal to lambda g with respect to y, which is 2y. And we have x minus 1 squared plus y squared equals to 25. All right, so solving this, here we get y equals 2 over lambda. And here we solve this for x. We get x equal 3 halves over lambda plus 1. Okay, then what we can do is substitute each one in here. So the 3 over 2 lambda plus 1 minus 1 in for x, that's just going to be 3 over 2 lambda squared. And y squared is going to be 2 over lambda squared is 25. So that's going to give us 9 over 4 lambda squared plus 4 over lambda squared equal 25. Multiplying through by 4 over lambda squared, we get 9 plus 16 equals 100 lambda squared. So we have 1/4, that's 25 over 100. And that gives us lambda to be plus or minus a half. Okay, now we'll go back and substitute that in here for the x and the y. When lambda is a half, then x is 3 over 2 times a half plus 1, and that is 4. And y is 2 over lambda, so that's 4. So we have the point 44. When lambda is negative a half, we have x is 3 over 2 times negative a half, that's minus 3 plus 1, is negative 2. And then y is 2 over negative a half, which is negative 4. So we get negative 2, negative 4. Well then, we find all our x, y's, and lambdas. We substitute them in for f. And here we get positive 25. And f of negative 2, negative 4, when we plug it into the original function, is negative 25. So this is the min, and this is the max. And if you look back, well, we didn't do this example, but I'll show you that in the example homework problems. If you look back at number 48 in the previous section, that's the same as 36 in this section. I'm going to show you another way to do that. So look at the example homework problems to get some more examples.